Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 2.2, Complex Solutions to Quartics. So I'm pretty sure you have not solved a quartic before, or if you have solved it via the remainder theorem. To be honest, solving quartics are not that difficult in comparison to solving cubics. There's a slight difference. One thing to note is no matter what polynomial you're trying to root, the number of roots always equal to the highest power. So if you're solving a cubic, you get 3 roots. If you're solving for a quartic, you get 4. You don't need to know anything further than a power of 4, so you would always only have 4 roots maximum. Next things, for the quartic that you're ever gonna see, you'll get them with real coefficients. That means that you have a real function, which means that the sum of all of your roots must be real. And from then, we can deduce that all complex solutions has to be in conjugate pairs. So for solving quartic, it's not that straightforward, but most of the time they'll tell you one of the solutions if it is a complex root. And also in the future, when I get to the algebra part, then we'll learn a bit more about cubics and quadratics and how their roots actually interact with the coefficients. For now, let's start by using the remainder theorem, or if it's given to you, then do use it. So given that 2 is a solution, we know that x take 2 has to be one of the factor of this whole thing, and you can check by remainder theorem, sub in 2, and you should get 0. So let's do a long division of x to the 4 plus x cubed take 2x squared plus 4x take 24. So when we do that, we get x cubed and take 2x cubed, that gives us 3x cubed, take 2x squared, then we add 3x squared, which will give us 3x squared, then minus 6x squared. That would yield us 4x squared plus 4x, sub in plus 4 x, and just actually plus 4x, yeah, that's fine, 4x, then we get minus 8x, that give a total of 12x, take 24, and so we have the last number as at 12. From this, we know that we have a cubic, which is a lot easier to deal with. So normally how you do this is to do remainder theorem, which is what I'm gonna do anyway. So if you spend enough time trying all the values, you should get 3, minus 3 rather, should be one of them, because I constructed this question by myself. So this is negative 12 plus 12. If you do try enough times, you should be able to get minus 3 rather. So x is minus 3 is a root, so you get x plus 3 as a factor, and you do long division again. Yeah, you're not that equipped to do cubic or quartic just yet because you didn't learn a certain coefficient relation. However, it doesn't mean that you can't do it. So with that, you can just do the good old thing again. Then this gives us 0, so we add 0x here. And finally for x plus 12, we can just add 4. And that should give us the answer. So x squared plus 4 has to be equal to 0. And so when you actually rearrange, you get that x is plus or minus the square root of minus 4, which is just plus or minus 2i. With that, we have the first solution given as x is 2. We have the second one that we used the remainder theorem to do, which is minus 3. Then we have one that we just used the remaining equation to just find, which is plus or minus 2i. And once again, as expected, the imaginary value or the complex root come in a conjugate form. So for tips on doing complex roots, there are a lot of different approaches that you can deal with these kind of questions. Remainder theorem is only one of it, and the root approach that I will teach you on chapter 5.1 will be much more useful and probably more applicable to many other roots, because so far you can only do roots, complex roots that only have one imaginary component without a real part. With the root approach, you can do any complex roots. However, that will have to wait, but it's definitely doable in the future. And also, when you are given one complex numbers, make sure you use the conjugate pair. And especially when the question gives you one of the roots being, say, minus 2i, then you will know immediately there is a root plus 2i. Or even if it's, say, a 1 plus 3i, then you know there is one that is 1 minus 3i. And it always works if you have real coefficients. So finally, it's time to do a bit of practice. There are two questions here that I have set up. I formulated them myself, and so I know the answer. You have a few seconds to pause the video if you want to have a go on a piece of paper yourself, and I will show you the answer in 5, 4, 3, 2, 1. Here are the 4 roots of the two questions. Note that there are complex conjugates for both of them. And that wraps up this video. I hope you've learned something. If you have any questions, do leave it in the comment section below. And I shall see you on my next one.